Okay, guys. This is one of the circumstances where I am out sick. I'm sure you guys heard my voice on Friday, not getting, not sounding very good when I was giving my lecture. But the show must go on, so we've got to keep doing this. So we're going to continue with simple pendulums, and I apologize. I know you guys prefer me doing it pencil to paper, but this is all I've got. I don't have my document camera at home with me, so we're going to have to do it using the iPad. We're going to do a real quick review of simple harmonic motion based on what we did last week. Then we're going to do a force body diagram of a simple pendulum. Then we're going to talk about the small angle approximation, and that's actually how we're going to derive our simple harmonic motion from a pendulum. And then then we're going to come up with a period of a simple pendulum, and if we have time, if it feels right, then we're going to go on to a solid pendulum, not just a simple pendulum. So, going from there, imagine we have a surface up here. And from our surface, we have our pendulum hanging down. All right, and it has a length of L. And it has a mass of M. Okay, it's the end of our bob. And it is offset from the vertical as good as we're going to get our vertical. And this right here gives us an angle of theta. All right? This is suspended by a very light string that has an insignificant mass, but there's a significant mass down at the bottom. So really all we're worried about is, we're really just worried about this thing down here and how it's swaying back and forth. So, before we discuss that too much, I want to do the quick review of simple harmonic motion. Remember we had, simple harmonic motion was a situation where we have the second time derivative of something's position, dt squared, is equal to negative the angular frequency squared times its actual position. And this lends us to a solution. One of the possible solutions of this is where x of t equals a cosine omega t. And then dx dt would equal negative omega a sine omega t. And that would give us, okay, and then that would also lead to a second derivative, dt squared, which would give us a negative omega squared a cosine omega t. But this right here is the same thing as our x. And so that gives us, that gives us our omega right there. And that's how we get the simple harmonic motion. So, right. So, there's that. So real quick, those are our equations for our simple harmonic motion. Now, what we're going to do now is we're going to do our force body diagram of our pendulum. Okay, so here's our pendulum. And with this pendulum, we're going to draw our bob again. We're going to draw this bob over here. Okay, our pendulum has its string angling up to the edge over here, tension. Okay, and it's going to have gravity right there. Well, there's definitely an acceleration acting on this, but we're going to extend this tension out through the plane here. Not through the plane, through this line. And that's probably a little too light for you guys to see, so let's try a little darker color here. There we go. And if it's hanging by this angle theta, then that's also the same as this theta here, as that angle theta. And that this bob is going to experience a force. It's got two portions to this gravity. It's got a portion of gravity that's in portion of gravity that is in this direction. It's got a portion of gravity that's in that direction. Well, this right here is going to be equal to the tension because it's not accelerating in the direction of the tension. It is going to be accelerating at a particular point back down in this direction. And this value right here is the net force on it. So this net force is going to equal to ma, but this force right here is just mg sine theta. So mass times acceleration of our bob at any particular point away from the center point of the swing is mg sine theta. Okay, but if we want to get this in terms of theta, then we know our acceleration, the acceleration of something, is equal to its angular acceleration times the radius. So we can take our angular acceleration, and now all of a sudden we're going to have some sort of relationship to theta. So this means that alpha equals our acceleration divided by our radius. So we're going to bring that over here, and we're going to have our mg sine theta. I'm switching it around here. Is going to be equal to, well, we're going to plug this in where our acceleration is. So that's going to be mass times alpha times radius. But the radius here for this thing is just the length of the pendulum. So we're going to switch that up to an L. So now all of a sudden we can rewrite this so that our angular acceleration, alpha, equals, well, our masses are going to cancel, and alpha is going to equal g over L sine theta. And this leads us to a really nifty tool that we're going to get to use. Or actually, another way of writing this then is that if this is acceleration, this is also d squared theta over dt squared equals g over L sine theta. Now, this does lead us to a really nifty tool that we're going to use. So this is going to be a bit tedious, so I'm going to have you guys take out your calculators. And here's what you're going to do. I want you to make this column. You're going to make theta in degrees. Okay. You're going to have theta in radians. Okay. And then you're going to do sine theta. All right, and I want you to do it for these angles. You're going to do it for 30. You're going to do it for 20, 10, 5, 4, 3, 2 degrees, and 1 degree. Okay, so right now I'm going to give you some time, give you a couple minutes to fill this out. So I'm going to give you a pause. Okay, and then I want you to pause the video and fill this out. So 3, 2, 1, pause. Okay, hopefully you've had time to fill this out. What you're going to find, so if you convert all these radians, we start getting these. So this is going to be 0.5236. then we're going to get a 0.3491 and a 0.1745, and then we're getting a 0.08727 and a 0.06981, 0.05236, 0.03491 and a 0.01745. And that's just hideous down there. Uh, 0.01745. All right. So now the task is find your sine. Well, the sine of sine of 30 is 0.5, right? 0.5000. It's 1/2. But then 20 degrees, 0.3420. 10 is 0.1736. Well, and there's the rest of them. And as you notice, as you go down to even 1 degree, that to 5 significant digits, that sine of theta and theta in radians are the same. That we can make this approximation that if our theta is pretty small, that sine theta actually equals theta. That they're the same thing. So we can make a pretty valuable approximation here, and a pretty valid approximation, that theta is approximately equal to sine theta for theta less than 10 degrees. So what do we do with this? Where do we go with this? Well, we get back to our formula here, where we had d squared theta over dt squared equaled g over L sine theta. I think that would equaled negative g over L sine theta. Well, but we want this to look like, but with our approximation, this becomes negative g over L theta. Well, doesn't this look a heck of a lot like negative omega squared theta, which is what we really want our solution to this to be? Okay, so if we do that, that just means that omega equals the square root of g over L, and the period of our pendulum is equal to 2 pi over omega, okay, or it equals 2 pi square root of L over g. And this is how long it takes for a pendulum to swing back. And we're actually going to try this when we have some free time in class. We'll set up the pendulum and we'll swing it. So, okay, so that is a period of a simple pendulum. So it sounds like we're going to have time. So it looks like we have time to move on to a physical pendulum. So, because I can cut out a lot of the review here. So, imagine if we have, instead of just having a pendulum from a bob, we have a point fixed in space. Okay, now imagine that we have, instead of a bob at the end of a string where we have all of the mass focused down at the very end, where it's the easiest case to study, we now have a solid pendulum, a physical pendulum, a thing that is sliding or that is rotating on its own. So we're going to take this stick, and it is, or a rod of length L, if you will, and it is rotating about this point right here. So it's sliding around it, or it's at the very end of it. Well, this whole thing has a length of, we'll call this whole thing a length of L. But when it is off at an angle, so we're going to create a vertical line here. All right, so we have our vertical line that is rotating through. Right? And here's our theta that it is rotated through. Now, the mass of this thing, we have right here in the center of it, we have our center of mass, okay, of our rod. And the center of mass of the rod is where, you know, we learned that the gravity acts through the center of mass of any particular object. So the force body diagram on this thing is going to be this still has its mg pointing down. Let's see if I can get, I don't know if that worked well. So I'll have to use a different tool here. Okay, so here's our mg acting down, and we have two components to it, of course, just like we always have. We have the force in that direction, and we have the force in this direction, and this one right here is our mg sine theta, just like with our regular pendulum. Okay. However, this force is acting at this point up here. So it's really acting in that direction on the center of mass, which means we treat this force acting on the center of mass as if it's acting on a torque based on this distance here. Okay, where's the torque acting on the center of our pendulum. So what we really get here, instead of mg, we have to do a rotational version of this, which is fine. We know that torque equals our radius vector crossed with our force vector. Okay, and this is going to equal I alpha. Well, our radius times our force vector is going to equal d times mg. Okay, because our radius is d, our force is mg, but anytime we cross two vectors, we also have our sine theta involved, and that equals I alpha still. Okay, or alpha equals dmg. Actually, that should be negative because it's restoring. Okay, negative dmg over I sine theta is now what our acceleration for our swinging rod. Okay, we can still make the same approximation that our sine theta is approximately equal to theta. So we can rewrite this as, okay, where alpha will become d squared theta over dt squared equals negative dmg over I times theta. So all of a sudden, instead of having just a simple g over L, now we have we have a more complicated version of this, and this is actually the general solution towards a swinging object like this, where omega squared equals dmg over I, okay, or our omega equals square root of dmg over I, and our period, I'll write over here because I've got more room over here, and our period, actually, sorry for the jolt there, but trick of doing things digitally is I can still move stuff on the screen. So our period here is then 2 pi square root of I over dmg, and so that is the period of our physical pendulum, and we have a solid thing. Where this d, remember, this d is the where d equals the radius to the center of mass from where our object is suspended. Okay, now we're going to simplify this a little bit, and I'm going to take this drawing, and we're going to sort of combine these two pendulums. So imagine if we have we suspend our so we're going to suspend our pendulum. We're going to take this pendulum and do the same sort of treatment to it, except now we have our pendulum is the same rod, except it is now extended to. I gotta do a little rotation here to it. So just a minute. Okay, so it's going to look like that, and our center of mass is still right there. All right, but what we do with this, instead of, now we know that if we're extending out down this line, then now what am I trying to say? This is still rotating about a new point. Instead of being right here, though, it is now up here. So what do? We use the parallel axis theorem. I equals ICM plus md squared, which is the distance from the center of mass. Okay, and we plug this in to our period. So our period would then equal, let's keep these separate, our period would then equal 2 pi times the square root of this big thing, which is our new center mass, I cm plus md squared, okay, all over dmg. Well, so here's another really cool approximation that works with this. Because the length of the string right here, okay, so the length of the pendulum compared to the radius of the center mass of this thing, this isn't very long, and we're squaring it. So this goes to 0 for ICM, and we are left with md squared over dmg. Well, that cancels with that d, and that m cancels with that m, and so we're left with d over g, but d was the length of the string, and so our period becomes 2 pi square root of L over G, which should look really familiar because that's the length we had of a regular pendulum. So if we extend our pendulum, if we extend our pendulum down from our length here, then it really just becomes a regular pendulum again. When it doesn't really matter what kind of object we have here, if it's extended from the top. So that is our physical pendulum, and I do believe, ladies and gentlemen, that this finishes our lecture for the mechanics portion of AP Physics C. So I'm going to finish by including on Edmodo all of your the remaining assignments for these lectures, these pendulum lectures, and it's time to start cracking and getting ready for our final, and then we're going to start on our electricity and magnetism. So peace out, and we'll see you next time.